Hello and welcome to lecture 26 of analog integrated circuit design. In the previous two lectures, we looked at models for thermal noise and flicker noise in a resistor and MOSFET. In this lecture, what we will do is to see how noise can be scaled in a circuit. That is, if we have a circuit with a certain functionality, we would like to have the same functionality, but with a smaller noise, and there are systematic ways of doing that. That is what we will look at here. Let me take the example of the amplifier I had earlier, and I will use this simple biasing scheme, although it is not required. Just for simplicity, I assume that the transistor is biased with a fixed VGS, an increment Vi is applied over it, and we have a resistor in the drain, and this is a common source amplifier with a gain minus GMR. Okay. Let us say this MOS transistor has a width W and a length L. Okay. Now, let me take an identical circuit W by L and R. Okay. And what I do is, I will connect the corresponding nodes of the two in parallel. Okay. Now, it is very easy to see that the functionality has not changed. The gain from the input to the output will still be exactly minus GMR. There are many ways of visualizing this. One way to think about it is that you imagine two identical circuits with identical inputs everywhere, okay, VGS and Vi. If that is the case, let us say you have two identical circuits. Here I will show it more abstractly with a number of nodes. The two circuits have the same input. Okay. In that case, the internal nodes will be exactly at the same voltages in the two circuits. This will be at the same voltage as that, this will be as at that, and so on. Similarly, here the gate voltage is the same. This circuit has only two nodes, the input and the output node. The output node voltage will be exactly the same in the two circuits. So, we can connect the two circuits without affecting the operation of the circuit, because they are at identical voltages. I can just connect them together. Okay. I can do this and nothing will change in the circuit. So, from this it is very obvious that however complicated the circuit is, if I take two identical circuits and connect the corresponding nodes together, I will have the same functionality as before. Okay. So, this new amplifier also has a gain of minus GMR. Okay. What does change though? We can see that this is equivalent to having a transistor of width 2W and a length L and a resistance R by 2. Okay. In this circuit, it is very easy to see that the noise current from the resistance has doubled. Okay. It is 4 kT divided by R by 2 instead of 4 kT divided by R in the original circuit, which is just that much. Okay. Similarly, the noise from the MOS transistor, what has happened to it? We see that the current in the MOS transistor has doubled, right. We have the same VGS and twice the width. So, the current will double and that will double the GM, okay. That will double the transconductance of the MOS transistor, because we have the same VGS and we have twice the width, the transconductance is doubled. So, this noise current, which is 8/3 kT GM in the original case, will become 8/3 kT times 2 GM. Okay. When I say noise is doubled, I mean that the noise spectral density is doubled. Okay. So, originally we had a resistance R, and in the noise picture 4 kT by R, and the noise of the MOS transistor 1/3 kT GM flowing into R. So, the output voltage noise spectral density was 4 kT R plus 1/3 kT GM R square. What do we have in the new circuit? We have 4 kT divided by R by 2. Okay. So, it is 8 kT by R, and similarly instead of 1/3 kT GM, we have 1/3 kT times 2 GM, which becomes 16 by 3 kT GM, and this resistance is not R, it is R by 2. So, if you look at the voltage noise, it will be 4 kT R by 2 plus 1/3 kT GM R square also divided by 2. Okay. So, if the first circuit has a certain voltage noise SVO, that becomes SVO by 2, that is the noise spectral density divides by a factor of 2 when we double the circuit. When I say double the circuit, I take two identical copies of the circuit and join the corresponding nodes together. Okay. Now, I have taken a very simple example, but this turns out to be universally true. Again, it is very easy to imagine two identical circuits operating with identical inputs, and in fact, for noise calculations we do not have to consider the inputs. Now, each of those components in each circuit can have noise. Okay. When you connect the corresponding nodes together, what happens is that let us say we represent all the noises by equivalent current sources in parallel. The current sources will appear in parallel. Okay. The noise current sources from the first circuit and the noise current sources in the second circuit will appear in parallel with the corresponding matched elements. Okay. So, the spectral density of the current noise source will double, right, because the noise in the first circuit and the noise in the second circuit are uncorrelated from each other. The spectral density will simply double, but the impedance has become half, because with every element in the first circuit there is another element from the second circuit in parallel. So, whatever impedance each branch has, it has become half of the original value. Now, what is the output voltage noise spectral density? It is equal to the current noise spectral density times some impedance squared. Okay. So, the current noise has gone up by a factor of 2, impedance has gone down by a factor of 2, impedance square has gone down by a factor of 4 consequently. Therefore, the product goes down by a factor of 2. So, if you take two copies of an identical circuit and connect the corresponding nodes together, what will happen is that the voltage noise spectral density at every node will reduce by a factor of 2. Okay. Now, this does not have to stop at a factor of 2, or the factor does not even have to be an integer. So, if you take two circuits, one of which is a scaled version of the other, let us say scaled by some factor n, the noise voltage spectral density will also be scaled down by a factor of n. Okay. And this is known as noise scaling. Let us say I have one circuit with R, C, L and MOS transistors. Let us say the MOS transistor width I denote by W. Okay. This is just an abstract representation of some circuit, and I consider the noise at some node, and let us say that is SVO. Okay. Now, let us say instead of R, what I do is I connect n of them in parallel. This is a way of thinking about it, but this works even if n is a non-integer. Okay. So, this becomes R by n. Capacitances, n of them in parallel will be NC, inductances, n of them in parallel will be L by n, and MOS transistors, n of them will parallel will have a width of n times W. Okay. It will have the same length, that is assumed. So, the noise of this will be SVO divided by n. So, this is a systematic way of scaling the noise of a circuit, and as I explained earlier, if I take these two circuits, the noiseless versions of them, and operate them with exactly the same inputs, the node voltages will be exactly the same in the two circuits. This is most easily imagined by starting off with the first circuit, and then you take an identical copy and operate them with the same inputs. Now, in the two copies, the corresponding node voltages will be exactly identical. You connect the corresponding nodes in parallel, what you will get will be a scaled circuit by a factor of 2. Okay. Now, because you are simply connecting nodes which are of the same potential, nothing else will change in the circuit, and the functionality of the circuit will remain exactly the same. And I illustrated that with an amplifier. I had a MOSFET of a width W and a resistance R. I doubled the width, I doubled the resistance, and my functionality remains exactly the same. I was getting a gain of GMR initially, and I get the gain of minus GMR from the new circuit as well. Okay. Now, what else does change in this circuit? From the power supply, or in general the currents anywhere, I will consider the power supply because that is what determines the power dissipation. So, let us say this is VDD and that draws a current I sub, let us say. What is the current drawn from this? It is easy to see that every branch current in the new circuit will be n times the branch currents in the original circuit. So, the current here will be n times I sub. Okay. So, scaling for noise, the noise voltage spectral density is 1 over n times the original, the power dissipation is n times the original, okay, and the functionality, that is the voltages in the circuit. Let us assume that we are interested only in the voltage transfer functions. When I say voltages, I do not mean the noise voltages, I mean the signal voltages will be identical in the two cases. Okay. So, this is a way of systematically taking some circuit and then reducing its noise without affecting the functionality, and you will encounter this scenario very frequently. In fact, let us say you have some circuit, you have designed it, its functionality is fine, its gain let us say is fine, but it has too much noise. You have to scale up the circuit in order to reduce the noise. Okay. And this is a sort of dumb scaling, in that we are not doing anything intelligent with the circuit. We are scaling the circuit that we have to have less noise, and it also consumes correspondingly larger power. Okay. So, this is a given, and sometimes you may have to go the other way around, that is increase the noise. Now, usually the objective will not be to increase the noise. What happens is, you have some circuit and that is consuming too much power, and you have to reduce the power dissipation of that circuit. Okay. The way to do that is to scale up the impedance of every branch by a factor n, that is we go from right side to the left side in this picture. Then what will happen is, the power dissipation will reduce by a factor of n, and the voltage noise spectral density will also increase by a factor of n. So, while saving power, the noise will increase, and let us say the noise of this particular circuit is not very significant. In that case, you can live with the increase in noise, but you will be happy to take the reduced power dissipation. Okay. So, you will go both ways depending on whether the power dissipation is important or the noise is important. Okay. It is very important to know the systematic way of reducing noise. Now, we have looked at thermal noise in resistors and MOSFETs. It is the thermal noise current spectral density is 4 kT by R in a resistor and 8/3 kT GM in a MOS transistor. Okay. Now, the point is, both of them are proportional to the absolute temperature T. So, another way of reducing noise could be to reduce the temperature. So, let us say I want I have some voltage noise spectral density SVO, and I want that to be SVO divided by n. I want to reduce it by a factor n. So, what can I do? I can reduce the absolute temperature by a factor n. Now, this is not an easy thing to do. Okay. You will have to cool down the circuit, but theoretically it is possible. Let us say you want to reduce the noise by a factor of 5. Now, we are at 300 Kelvin at room temperature. If you want to reduce the noise spectral density by a factor of 5, you have to cool it down to 60 Kelvin. Okay. If you do that, then the noise spectral density will become 1/5 of before. Now, let us not worry about whether the circuit will really work at such a low temperature and so on. Let us just assume that it does. Now, there is an interesting calculation related to how much power this will consume. Now, how much power does it take to cool down a circuit? Of course, in practice it takes a lot of power. It appears that it will take a lot of power. What you will need is a refrigerator, but we will look at some fundamental refrigerator. Okay. I think all of you are familiar with the Carnot engine from thermodynamics, and usually you think of it as something that takes thermal energy and converts it to mechanical energy, and there is the very well known formula for the efficiency of a Carnot engine. It operates between two temperatures T2 and T1, and let us assume T2 is more than T1. Okay. Now, what does it do? It produces some mechanical output power P mech, and it wastes some power in the form of heat. Let me call it P heat, and that goes from the higher to the lower temperature. Okay. And the classical formula tells you that the efficiency, the mechanical power to mechanical plus the wasted heat is T2 minus T1 by T2. Okay. You know that only by cooling T1 down to absolute 0 will you get 100% efficiency. Okay. Now, what we want of course is not a Carnot engine that produces mechanical output, but something that takes mechanical power as input and pushes the heat in the other direction. That is what a refrigerator does, right. It pushes the heat from a lower temperature to a higher temperature, and that is why you have to put some work into it to be able to do that. Okay. So, in this case the input is P mechanical, and I will simply say that it transfers some thermal power P heat from T1 to T2. Okay. So, this is exactly the reverse of what a Carnot engine is. Now, it turns out that the same formula applies even in reverse. Okay. Now, what are these quantities in our case? Let us say I put some circuit which dissipates a power P d inside a refrigerator, and it is at this low temperature of T1 and the outside temperature is T2. Okay. I do this instead of putting this at the outside temperature of T2. So, T2 is my T in my previous expressions, and if I want to reduce the thermal noise by a factor n, T1 should be T divided by n. Okay. And what is P heat? It is equal to P d. Okay. Whatever power is being dissipated by the circuit has to be taken out, right. Exactly that much has to be taken out. That is when you can maintain it at a constant temperature. If you take out more heat than the circuit is dissipating, then it will eventually cool down, and if you take less heat than what the circuit is dissipating, it will keep heating up. Okay. So, for it to be at a steady temperature, the amount of heat taken out of this system from T by n to T must be exactly equal to P d. Okay. So, this P heat is P d, okay, and P mechanical is the external power that I have to drive, and that is what I have to find out. Okay. So, let me substitute in this formula. P d equals T2 minus T1, that is T minus T by n divided by T. Okay. And I have to calculate P mech from this. If I do the calculations, I will see that P mech is n minus 1 times P d. Okay. That just comes from some simple algebra on this relationship. Now, this is very interesting. So, what are the ways I have of reducing thermal noise? Let us say the circuit is consuming some PD and I have R and MOSFET and also other components. I will show only 2 of these for simplicity. So, the first thing I can do is circuit scaling, which says that I have to multiply every branch by a factor n. So, R becomes R by n and W becomes n times W, and this will consume a power of n times PD. Now, what is the alternative? I can choose to refrigerate this. Okay. Let me show the refrigerator outside this one, and inside this the temperature has to be T by n and outside is T, that is the assumption. It is the same ambient temperature at which the original circuits are operating. So, for me to sustain this condition, I will have to have a mechanical power input of n minus 1 times PD. Okay. This is an ideal refrigerator working according to the Carnot cycle. And what is the total power dissipated here? The circuit consumes PD and the mechanical power is n minus 1 PD. So, the total power is n times PD. Okay. We get exactly the same power dissipation as when you do circuit scaling. So, this is just an interesting thing. Normally, you would not try to refrigerate circuits, and in any case you cannot get this Carnot refrigerator with the ideal efficiency. The efficiency of an actual refrigerator will be much lower than this one. Okay. But it just illustrates the fundamental calculations and shows you that the circuit scaling is also a fundamental thing. Okay. So, whether you try to reduce the noise by refrigerating it or whether you try to reduce the noise by scaling it, you will end up burning n times the power when you want to scale the voltage noise spectral density by a factor n. Okay. Now, I said that normally you would not refrigerate circuits, but in special cases that is the only way that you have to reduce the noise. Let us say you have done noise scaling and everything that could be possibly done to minimize the noise in your circuit, then you still want to reduce the noise further, you have to cool it down. Okay. In some very special circumstances, usually let us say some amplifiers for radio astronomy and so on, you do have amplifiers which are cooled down, you do have circuits which are cooled down, so that their thermal noise is reduced. Okay. But normally you would not think of doing something like that, you would just do the noise scaling. Okay. Now, while we are on the topic of noise scaling, we can also look at other scaling rules. Let us say we look at frequency scaling. Now, again I will illustrate it with we have already analyzed the noise of this. We know that the output noise variance is kT divided by C. Okay. Please keep in mind, previously in the noise scaling part we were talking about the noise spectral density. Okay. And here we are talking about the variance of noise or the mean square noise. Now, the two are related, but not exactly the same thing. So, please be aware of what is being reduced when we say that we reduce noise, etcetera, etcetera. Okay. So, the mean square noise that we get is kT by C, and we can change the bandwidth of the circuit. So, let us say bandwidth goes to 1 over n times the original bandwidth, and similarly here I can reduce the bandwidth. Instead of modifying the capacitor, what I will do is I will modify the resistor, okay, NR and C. Now, the voltage transfer functions of these two circuits are exactly the same. Okay. They have a bandwidth of 1 over n times 1 over RC radians per second. Okay. but what is different between the two is noise. This circuit has a noise of kT divided by NC, okay, and the lower circuit has a noise of kT divided by C. Okay. Just to distinguish it from the previous scaling, previously we were trying to keep the functionality the same, but reduce the noise. Here we are trying to change the functionality, in that we are trying to reduce the bandwidth by a factor n, and we want to see what happens to noise. Now, there are different ways of scaling the bandwidth. One is to play around with the capacitances, one is to play around with the resistances. I have taken the example of a first order RC circuit which has only one resistance and one capacitance, but this is a universally true rule. Okay. As you can see from this, we can generalize and say that we can scale the bandwidth by a factor alpha. Okay. So, what it means is that if one of the circuit has some frequency response like this, and the other circuit will have exactly the same frequency response, where this is alpha f. Okay. So, let us say we take alpha equal to 2. What I mean is, let us say this peak occurs at the peak of some transfer function, it occurs at some frequency f naught, let us say 1 megahertz. If alpha equals 2, in the scaled circuit exactly the same shape will be preserved for the frequency response, and the peak will occur at 2 megahertz. Okay. So, as I said, there are two ways of achieving this. Again, I will take my original circuit, let us say it has some resistors, transconductors and capacitors. Okay. And I can make the frequency response scale by alpha. Okay. That is, f goes to alpha f. To do this, I can have the resistance to be R, the transconductance to be Gm, and the capacitance to be C by alpha. Okay. Alternatively, reduce the resistance by factor alpha, increase the transconductances by factor alpha, and keep the capacitance to be exactly the same. Okay. Now, this is known as constant C scaling for obvious reasons. The capacitance is kept constant, and this is known as constant R or constant conductance scaling. Okay. Now, both of these will give you exactly the same frequency response. Okay. This and that will have alpha times scaled up frequency axis compared to that one. Okay. If alpha is a factor of 2, so that means that whatever is happening in the original circuit at 1 megahertz will happen at 2 megahertz in this circuit and that circuit. Okay. But the difference will be in the noise. So, let us say the integrated noise between some nodes of this is V n square. Okay. The integrated noise of this circuit will be alpha times V n square, and the integrated noise of this circuit will be V n square itself. Okay. Now, this is illustrated by the example. So, this is constant C scaling, and that is constant R scaling. Okay. So, in constant R scaling, you keep all the conductances and transconductances to be the same, and you change the capacitances to modify the frequency response, and in constant C scaling, you keep the capacitances the same and modify all the conductances and transconductances to scale the frequency response. Okay. Now, these two again are very widely used. Many times you want to have blocks like filters, which maintain the same frequency response, but different bandwidths. Let us say you want a Butterworth filter at 1 megahertz or 2 megahertz or over a wide range of bandwidths. Now, you have to decide which kind of scaling you want to use based on what you want to happen to the output noise of the circuit. Okay. So, to summarize, to do noise scaling, scale all elements by a factor n. So, this means that you will have n of them in parallel. Okay. That is an easy way of visualizing it, but as I mentioned a couple of times earlier, n need not be an integer. So, this means that a conductance will become n times the conductance, a transconductance becomes n times the transconductance, a resistance obviously from this becomes 1 over n times the resistance, and an inductance becomes inductance divided by n, capacitance becomes n times the capacitance, and so on. So, if you have a MOSFET of width W, it will have n times the width in the new circuit. Okay. If you do all of this, the voltage noise spectral density at any point in the circuit between any two nodes in the circuit will scale by a factor n, and currents everywhere in the circuit including the supply current let us say I have some branch current I k. This is not just the small signal current, it is the total current will become n times I k, and this obviously is true for the supply current as well. So, the power dissipation becomes n times the power dissipation of the original circuit. Okay. So, this is a way of noise scaling, and scaling it without changing the transfer functions in the circuit. Okay. You consider any transfer function in the old circuit and the new circuit, they will be exactly the same. Okay. This is again most easily imagined by imagining identical copies of the circuit and connecting them node by node. Okay. If you have identical copies with identical inputs, when you connect them node by node, nothing changes, no voltages change, but the impedance would have become scaled. Okay. This, by the way, is also called impedance scaling, because all branch impedances Z k have become Z k divided by n. Okay. Now, we sometimes have to do bandwidth scaling. What we mean by that is, we preserve the transfer function, it should get scaled to h of f by alpha. So, this means that if the original transfer function was something like this on a scale f, the other one will be stretched out on the scale f. If I plot it on the same scale, that is what it will look like, okay, but the shape will be preserved. And in this we have different possibilities: constant capacitance scaling. This means that all C's will remain at C and all conductances will be n alpha times the conductance, and all transconductances will also be alpha times the transconductances, and in this case the noise turns out to be the same. Okay. If original noise was some value, the noise mean square value, the new mean square value of the noise will be the same. We have an alternative which is a constant conductance scaling. In this case, we reduce the value of C by alpha, but keep G and Gm conductances and transconductances to be exactly the same. Okay. In this case, what happens is that if the original circuit had a certain mean square value of noise, voltage noise, it will be alpha times the old value in the new circuit. Okay. So, which one you choose depends on the constraints that you have. That is a summary of systematically scaling noise in a given circuit, depending on whether you want to preserve the functionality or you want to scale the bandwidth without changing the shape. Okay. And you will have to do this very frequently when you come to circuit design, especially impedance scaling, because the first circuit that you realize may not be suitable for noise or power dissipation. Okay. In either of these two cases, you can alter the circuit without changing its functionality to either usually to reduce the power dissipation or to reduce the noise. Okay. Now that we have looked at the noise of components, in the previous few classes we have looked at models of components, their large signal behavior, small signal behavior, and noise mismatch and so on. So, it is now time to go and design our op amps, design the circuits that we want using transistors, okay, and other components. So, before we do that, we will do a quick review of the basic amplifier stages that you already know from undergraduate electronics courses. Okay. Now, the objective of this review will be, first of all, just a quick refresher, and also to look at effects that you may not have looked at before, especially something like body effect, which comes into picture predominantly only in integrated circuit design. Okay. Now, what are the basic amplifier stages that we know? The single transistor amplifiers are the common source amplifier, the common gate amplifier, okay, or the common drain amplifier, which is also called the source follower. Okay. The common source amplifier has its small signal input between the gate and source and the small signal output between the drain and source. The small signal gain of this is minus GM R. Okay. So, the small signal picture looks something like this. I will use the symbol of the MOSFET for the small signal equivalent in this case, and this is R, and the output will be minus GMR times Vi. Okay. Now, we can bias the transistor in various ways, okay, and usually a constant current biasing is preferred to constant VGS biasing. This is because of the sensitivity. When we say sensitivity, we are talking about sensitivity to the parameters of the component or the MOSFET. Now, if you bias a transistor at a constant VGS and let us say the threshold voltage changes or mobility changes, the GM will change by a certain amount. Now, let us say you bias it at a constant current, and there are ways to do that. Then if the threshold voltage or mobility changes, there can be a change in GM, but it will be much smaller. Okay. Now, if you look at the ideal square law model, if you change the threshold voltage, but bias the transistor at a constant current, there will be no change in the transconductance or GM of the transistor. And if you bias it in constant current and the mobility changes, there will be a change in GM, but it will be much smaller than when you bias the transistor with a constant VGS. Okay. So, the constant current biasing is what is preferred. I will quickly show an example. So, one way of making a common source amplifier with a constant current biasing is to use current mirror biasing. Okay. Let us say M0 and M1 are identical, and this is some R bias that is very large, and we AC couple a signal to the gate of M1. Now, this is biased at a constant current I naught. So, the gain minus GMR from Vi to the output will not be affected too much by the changes in threshold voltage and mobility of M1. Okay. And there are other ways of biasing the transistor at a constant current. Again, these you know from your basic circuits courses. Let us say you connect a constant current source at the source of the MOS transistor and bypass it with a large capacitor for high frequencies. You bias the gate with a resistive divider and apply your input. Okay. This is the supply voltage. The output will be again minus GMR times Vi. The signal is AC coupled to the gate. Okay. So, these are different biasing strategies. You can have even other types of biasing if you wish to have that. Okay. Now, in this case I am only interested in the small signal performance. I just showed this to quickly illustrate how the transistor can be biased. Here again I show only the small signal picture. Okay. So, what will be the output? It is minus GMR times Vi. So, the gain is minus GMR. Now, if you include the output conductance of the MOS transistor, it is really minus GM R parallel RDS or minus GM divided by G, which is the conductance corresponding to this element, plus GDS. Okay. Now, a lot of times we would be operating in the regime where R is much smaller than RDS. So, the gain is approximately GMR, but the gain really is influenced by RDS as well, and that is something that has to be taken into account. So, beyond that there is not much to the common source amplifier. Okay. The input resistance looking in here is infinity. If you have some biasing network, that may contribute to the input resistance, and the output resistance looking into the MOSFET is RDS. Okay. And finally, what is the effect of body effect or the bulk transconductance GMB in this circuit? I have shown the 3 terminal symbol here, but the source is at a fixed potential and the bulk will also be at a fixed potential. Okay. Now, it may be at a different potential for DC, but small signal wise that is also at ground. So, the small signal VBS equals 0. So, that means that GMB times VBS, which is the effect of the bulk transconductance, that is also 0. Okay. So, simply the body effect does not influence the common source amplifier. Okay. So, that is all that is there to it. Now, let us go on to the common gate amplifier. Now, what is the common gate amplifier? Again I will ignore the biasing and look at only the small signal picture. The common gate amplifier has its gate connected to incremental ground and it will have a load connected to the drain. It could be a resistor. So, let me just show a resistor for simplicity, and it will have an incremental current input II. Okay. So, again there is some bias current, this is only the increment. Now, what is the functionality of the common gate amplifier? It is a current buffer with the output current IO equals II. It is a current buffer with unity gain. Now, what is the use of such a thing? What it does is to take a potentially bad current source and turn it into a better current source. Okay. So, that we can look at by examining the input and output resistances. Now, first of all, when RDS equals infinity or the GDS of the transistor equals 0, the resistance looking into the source of the transistor, the input resistance is just 1 by Gm. Okay. I have not included body effect, I will do that later and then see what the effect of that is. This is 1 by Gm, and the impedance looking from the drain, that is the output resistance, is infinity. Okay, because you have only a current source here, and if you do not have any source on this side, you will see an open circuit. That is regardless of the value of the resistance of the input source Rs. Now, when RDS is not equal to infinity, R out will be Gm RDS Rs plus RDS plus Rs. This is something that you know from basic circuit analysis. Okay. Now, what will be Rin? Rin is still approximately equal to 1 by Gm, but this is true as long as R is of the same order of RDS. Okay. So, this point, this is not true if R happens to be much more than RDS. Okay. Now, this can be imagined very simply by considering R to be an open circuit, R to be infinity. Okay. If R is infinity, we have an open circuit in the drain. So, clearly any incremental current that you inject here cannot go anywhere. So, the incremental current going into the source has to be 0. So, that means that Rin is infinity as well when R equals to infinity. So, we will not work out the exact expression, you can take it up as an exercise and please do that, but the result of that should be that when R is rather small and when it is comparable to RDS, then Rn will be 1 by Gm, and when R is much more than that, it will not be equal to 1 by Gm, it will be some very high impedance. Okay. But we will assume this condition to be true, and under those conditions it provides a small input resistance and a very high output resistance, which is exactly the quality you want from a current buffer. Okay. So, if you have a current source of with an internal resistance of Rs, it will look like a current source of the same value, but a much higher internal resistance. Okay. Now, the interesting thing is what happens to this circuit with body effect. Now, clearly here you can expect something interesting to happen, because the source is not at small signal ground, but the bulk will be at small signal ground. I will just say Gm, but it means that it is multiplying VGS, and similarly I also have GMB, okay, and the bulk is at ground as well. This is bulk, source, drain and gate, and normally I apply my input current here. It will have some internal resistance Rs, and there will be a load resistance over there. Okay. So, without this we have already determined the answers, that is the output resistance is high, it is Gm RDS times Rs plus RDS plus Rs and so on. What happens due to GMB? Now, in this case the analysis is very simple, because this is VBS, okay, and let me call the voltage at this node Vx, VGS equals minus Vx and VBS equals minus Vx. So, these two control sources are in parallel and they are multiplying the same quantity minus Vx. Okay. So, effectively what we have is a current source which is Gm plus Gmb times minus Vx. Okay. That is because in this circuit VGS happens to be equal to VBS. So, Everywhere we have Gm in the original expressions, we have to substitute Gm plus Gmb, okay, because originally we just had Gm times Vgs, Vbs is exactly equal to Vgs. So, here we will have Gm plus Gmb times Vgs everywhere. Okay. So, what does this mean? The input resistance is 1 over Gm plus Gmb. This again assumes that R is not much more than RDS, okay. And R out, the expression for that will be Gm plus Gmb times RDS times RS plus RDS plus RS, okay. So, you can see that in this particular case, the body effect GMB is actually helping you. GMB is an additional control source in parallel with GM, and it simply adds up to GM in case of a common gate amplifier. It further lowers the input resistance and further increases the output resistance. And as you know, a current buffer is supposed to have a low input resistance and a high output resistance, and the bulk transconductance GMB actually helps you in this direction. Okay. Thank you. In the next lecture, we will look at the effect of body effect on the common drain amplifier or the source follower, and also look at other transistor level circuits such as the differential pair with which we can make op amps.